Alright. So we looked at our linear equations and two variables yesterday. Now we're going to do a basic introduction to functions. One of the biggest differences from moving to Algebra 1 to Algebra 2 is a focus on what we call functions. You get a little bit of it in Algebra 1, and then pretty much from now on, everything that we do has to deal with functions. Okay? So, sorry about that. Okay. So with functions, what we're doing is we're looking at every type of equation that we see, or even just sets of values, are going to be called relations. Okay. We're comparing something to something else. It makes it a relation. Okay. When we have a set of ordered pairs, if I have 1 point, if I have 5 points, if I have 1,000 points, if I have a line, which is an infinite number of points, all of those ordered pairs form a relation. We are comparing an x to a y. All right. Now, a domain is all of the x values that we have. Okay. So if I have 5 different points, then I could have up to 5 different x values. Okay, and that would be my domain. All the x values are the first component of the ordered pair. And the range talks about the second component, the y value. So if I had 5 different points, I could have up to 5 different y values. Okay, so domain and range. Okay, so domain is all of the x values of my ordered pairs. If I have any that show up more than once, I don't need to list them more than once. I only need to list them one time. Okay, so looking at this relationship here, I've got 4 ordered pairs. What are the values in my domain? What are the 4 values in my domain? 4, negative 4, 2, and 10. That's my domain. My domain is 4, negative 4, 2, and 10. Okay, 4, negative 4, 2, and 10. And a lot of times you'll see that listed in ascending order, so the lowest value first, negative 4, then moving up to 2, 4, and 10. Okay, but just understand the first component of the ordered pair, the x value. The range is going to be the y values. So what are my y values? What are my ranges?
9, 3, negative 5.
Good. And we don't want to repeat the 9. Even though it's there twice, I'm only going to write it once. And then I've got a 3, and I've got a negative 5. Okay? So all that's saying is that all of my x values are these numbers. All of my y values are these numbers. Okay? Nothing else. All right? So that's if I just have a list of points, a list of ordered pairs. Okay? It doesn't have to be ordered pairs. It could be relationships of input and output. Okay? So here, find the domain and range of the following relationship. I've got my input, or my first component, is animal, and the output, or the second component, is lifespan. So my domain is just going to be a list of all of these animals. Polar bear. I'm just going to abbreviate because I don't feel like writing them out. And cow, and giraffe, and gorilla, and kangaroo. That's my domain. It's just those 5 animals. Okay? My range is going to be all the different lifespans. Okay? Now, both polar bear and gorilla have a lifespan of 20 years, so I'm only going to write that once. And then I have the rest of my values for my range. Okay? So it can be numbers, it can be words, it can be letters, it can be cities, it can be states, it can be people, it can be grades, it can be whatever we want. Okay? We're comparing 2 things. That's what a relation does. It compares 2 things. The domain of the relation is the input, the first component, and then the range is the output. Okay? And we have a few other terms that we use to compare and talk about input versus output, first component versus second component. We also use, we'll talk later about independent and dependent variable. Now, we have a special type of relation called a function, and that's what we're going to spend most of our time dealing with is functions. And what makes a function special is that for any given input, okay, any given x value, any given first component, it always corresponds to exactly one output, okay, and one only, all right? And that's the difference between a relation, or that's what makes a relation a function, okay? All functions are relations, not all relations are functions, okay? So function is like a special type of relation, all right? So what we're looking at is basically, do my x values repeat? And if they do they give me a different number? If the answer is yes, then I don't have a function. But if every x value corresponds with a unique y value, then I have a function. All right? So first I'm going to look at my x values. Do any of them repeat? No. And since they don't repeat, then I know that each output is going to have, or each input's going to have a unique output. Okay? So yes, this is a function. Yes, this is a function. Each input corresponds with exactly one output. Now what I want you to notice, that was supposed to be a highlighter. Let's try that one more time. Erase. Highlighter. There we go. The 9 repeats on the output. That's fine. Okay? That's okay. I can have an output show up more than once. I could have one output for all of my x values. That's okay. What I can't have is an x value point to 2 different numbers. And I like to give an analogy for like test scores. Okay? So, Kale and Sebastian can both earn a 90 on a test. That's allowed. He can get a 90 and he can get a 90 separately. Alright? So that is 2 inputs, the people, corresponding to the same output, the score. There's nothing wrong with that. But what can't happen is Christina can't get an 80 and a 90. She can't get the same grade, or 2 different grades on the same test. So that's 1 input corresponding to 2 outputs. Does that make sense? Okay? So I can have 2 people with the same test grade. That's fine. But I can't have 1 person with 2 different test grades. Alright? So that's what makes it a function or not. Okay, so each input corresponds with exactly 1 output. Alright? So now, with equations, okay? A lot of the equations we're going to deal with are going to be functions, but there's something very unique about an equation that gives us a hint of whether or not it's going to be a function. So I want to show you a few things about these two, okay? Yesterday we talked about quadratics. What shape does a quadratic typically have? What did we talk about yesterday with the shape of a quadratic? Right? It's a U shape. Okay? So quadratics usually have this kind of a shape right here. Alright? So as I look at this, and I pick any point on this line, okay? So I have my x values down here, my y values down here, or on the left, okay? So it's my y-axis and my x-axis. Alright? I can pick any point on that line and look and see, okay, so if x is 3, there's only 1 y value that goes with that x. There's no other point where I have an x with a different y value for when x equals 3, or for when x equals 4, or x equals 5, or x equals 6. I go along every single point on this line, and that x value only shows up once. And it matches to a y value. Okay? Now, sometimes the y values show up twice. I have 2 x values with the same y value. That's fine. There's nothing wrong with that. Okay? Sebastian and Kale both got 90s on their test. Good job. Okay? I mean, I don't know for sure. I haven't graded the test yet. But it's an analogy. Okay? So, if you get a 90 on the test, 2 people can get a 90 on the test, but 1 person's not going to get 2 different scores on any given test. Alright? So, our quadratics are going to be functions. Okay? Is a relation a function? Yes. Okay, our relation is a function. right? Because every corresponding x value. All right. Now, this equation is a little bit different. What's the kind of the biggest difference between this equation and this equation? Not only that, I mean, we can rearrange them all over. That's going to, I mean, yes, it's different, but that's not like that big difference. Y has the exponent as well. Okay, or the y has an exponent. Okay, that's a really, really important distinction. Most of the time, we have equations in the form of y equals and then a bunch of stuff. Okay, and generally, when we have y equals a bunch of stuff, we have a function. But now I have y squared. This is the equation of a circle. Okay, this is the equation for a circle. So if I look at the circle and I place it in the coordinate grid, okay, I got a y-axis here, I got an x-axis here, and I pick an x value, okay, whatever that x value is. I see that I have this y value, but I also have this y value, which means that I have an input that's an x, but I have two different outputs that are possible. Okay, so since most of these x values correspond with two y values, no, it's not a function. Okay, because each x value, or most x values, except for two, there's only two that are the exception, are going to correspond with two y values. And so it's not going to be a function. Do you have a question? So, and the big thing to notice is that's going to be true for, let's say I have the equation y squared equals x minus 2. That's a parabola, but since it's y squared, it's turned sideways. So now each x value corresponds with two y values because I have any given x value on my coordinate grid and then two y values that match with it. So when you see that y squared, that's a big red flag, probably not going to be a function. Okay? But outside of that, as long as your y is not squared, probably going to have a function. I'm having a hard time of thinking something off the top of my head. Doesn't have a y squared that isn't a function. So that's kind of the big thing to look at when you're looking at an equation. A y squared is a big indication, not a function. But pretty much everything else we're going to deal with is. Okay? Most of the time we're going to have a function. Okay? Which leads us into what we call the vertical line test. All right? Hey, see this vertical line that I drew? See this vertical line that I drew? See how it ran through 2 points? And those were neither of those were functions. But I draw that same vertical line through my parabola, and it only ever touches at 1 point, and it is a function. That's our vertical line test. So if I draw a vertical line across my entire graph, and anywhere in my graph, if it ever touches more than once, then it's not a function. If it touches no more than once, then the graph is a function. So when we look at a bunch of different graphs here, okay, I have a linear equation. It's a straight line. No matter where I draw the vertical line, it only ever touches at 1 point at a time. So that means that every x value only corresponds once, okay, to each y value. Same thing with this horizontal line. No matter where I draw that vertical line, it only intersects once. So both of these are functions. Both of those are functions because they pass the vertical line test. Okay? Those both are functions because they pass the vertical line test. Pass the vertical line test. Okay? So when we have an equation, we look at the form of the equation and say, do I have an x squared or a y squared? If I have a y squared, it's not going to be a function. If I don't, it is. If I'm looking at the graph, I do the vertical line test. And I run that vertical line and see, is it going to pass the test or is it going to fail the test? All right? So here I have an ellipse. okay, which is an oval. All right? So vertical line test fails. Not a function. Not a function fails the vertical line test. Okay? Now, there is 2 points where it passes. If I drew a vertical line here, and I drew a vertical line here, it passes there, but everywhere else it fails. And it only needs to fail once. It only needs to fail once in order for it not to be a function. Okay? So even though those 2 passes, it fails everywhere else. If it fails anywhere else, it's not a function. Okay? So now what we're going to do is we're going to look at domain and range, okay, of graphs. We talked about domain and range when we listed ordered pairs, all the x values, all the y values. But now we have a graph. And I can't just list singular x values or singular y values because there's an infinite number of points here. So we're going to use our interval notation again. Just like when we had our interval of x is less than 2. Okay? So when we had our inequalities, this is a little flashback. Okay? A little flashback to our inequalities. When I had x is less than 2, that means I had all values from negative infinity up to 2. Okay? So I used interval notation, negative infinity to 2, to list all of those values. Or if I had between 10 and that's an x and 40. Okay, all values between 10 and 40. Let's put some or equal to in there. Okay, x is greater than or equal to 10. X is less than or equal to 40. Then my interval notation is all values from 10 to 40, and then I'm going to use those brackets instead. And on a number line, I've got 10, and I've got 40, and I've got closed circles, and I'm filling those in. Okay, that's my number line. It represents all of those numbers. Not just specific numbers along the way, every single number. Like 20, or 21.2753468, or 20 and 5/7. Okay? All real numbers between 10 and 40. So I need to do the same thing when I'm looking at domain and range. I'm going to be writing an interval notation. Oh, that's what I want. Okay? I'm going to be writing an interval notation based on what I see with the graph. What's the lowest x value and what's the highest x value? What's the lowest y value and the highest y value? So let's start with domain. Okay? So looking at this graph, what is the furthest left x value? Minus what? 3. That's the furthest left x value. Negative 3. So I have the point negative 3, 2. I want to focus on the x value of negative 3. Yes, ma'am. Go for it. Negative 3. Okay? What's my furthest right x value? 4. So I've got this point here that is 4, negative 4. Okay? Now, these are closed circles. That means those values are included. So am I going to use a parentheses or a bracket? I'm going to use a bracket. That's what I used on my number lines. I'm going to do the same thing here. I'm going to use a bracket. So all values from negative 3 to 4, that's my domain. Okay? So all of the x values are from negative 3 to 4. All the real numbers in between. All the fractions and the decimals and the rational and the irrational numbers between negative 3 and 4. Okay? So now let's look at range. What's my lowest y value? Negative 4. What's my highest y value? 2. And again with the brackets because I got the closed circles. Okay, those points are included. So that domain is all the x values, range is all the y values. Okay, so that interval notation is something that we do a lot. Okay, shows up in a lot of different things. Keep doing interval notation over and over and over. As we're dealing with a lot of numbers. Interval notation is that shorthand that lets us represent a lot of numbers. Okay. Now, what's the difference besides the shape? Besides the shape, we got a V shape versus a line. What's another big difference between this graph and this graph? There's two. Look at the endpoints versus continues. Okay, and it never stops. Goes on forever. What do we use to represent something that goes on forever? Infinity or negative infinity. Okay, so since I know those lines go on forever, I'm going to be including infinity and negative infinity in there somewhere. Okay, maybe more than once. So remember, that means it goes forever. So I've got infinity and negative infinity. So let's look at our domain first. All right, lowest possible x value. So I have this line, and it's going up and to the left forever. So it's going left forever, and it's going up forever. So if it's going left forever, what's my lowest value in my domain? Negative infinity, because it goes forever to the left. It's going forever up, but also to the left, and I'm only focusing on the left part. So it starts at negative infinity. And what symbol always goes next to the negative infinity? Parentheses. Always parentheses. That's true here, just as it was with our interval notation. Infinity always gets parentheses. Now I'm going to continue, and I'm going to the right, and I'm going up and to the right forever and ever and ever and ever and ever. So my domain here is negative infinity to positive infinity. So in interval notation, negative infinity to positive infinity. We also can refer to this as all real numbers. Okay, all real numbers. All right? All real numbers is my domain. That happens with a lot of functions. Our domain is all real numbers. Okay? So get used to that. It's not always, but with our linear equations, our quadratics, our cubics, our cube roots, some of our sinusoids, a lot of our functions have a domain of all real numbers. It's a really, really common one. Again, it's not all of them, but it's a lot of them. Okay? Especially if they're continuous and unbounded. So now let's look at range. Range. Okay? So now looking at this graph, what's the lowest possible y value? -2. Boom. Right there. -2. That's my lowest possible y value. Parentheses or bracket? Bracket. It's included. The only way you would know that it's not included is if they literally drew an open circle here. If they drew an open circle, then it would be parentheses. But it's included. It's unbroken. So we're going to use a bracket to say that -2 is included. It goes right up to -2, and it stops and bounces right back up. Okay? Now, we're going up forever. So what's the end point of my range? Positive infinity with a parenthesis. Okay, so my domain was -infinity to infinity. My range is -2 to infinity. All right. Questions on either of those? Okay. I think the last thing we're going to talk about is function notation. Okay. Function notation. Okay. So a lot of times we end up dealing with functions more because I don't really care so much about the line, but I care about specific values for the line. So we deal with stuff in function notation. All right. What that does is it takes your y, the variable y, and replaces it with f of x. They are the same thing. Okay? We can only do that when we have a function, but it lets us know right off the bat, hey, this is a function. Okay? So, to note that y is a function of x, we write y as equals f of x. So any equation that we had earlier, I don't feel like scrolling all the way back, but if I had the equation that y equals 3x plus 2, in function notation, I just replace y with f of x. But it means the exact same thing. It means the exact same thing. It's just indicating, hey, this is a function. And it allows us to evaluate for different parts of our domain. Okay? So y is a function of x. Y depends on x, and then I mentioned earlier dependent and independent variables. Okay? X is your independent variable. It's the thing that you're choosing, the thing that you're controlling. Okay? That's your input value. And then whatever you put in for x is going to affect what y is. So y is dependent on x. Y is our dependent variable. Okay? So the benefit of function notation is instead of saying, oh, I have this equation, y equals x squared minus 2x, solve for when x equals negative 3, which is a lot wordier. We have this shorthand. So I have this function, and I want to find f of negative 3, which means, hey, negative 3 is x. Solve for when x is negative 3. So we just take our function and say, well, if I have the function f of x equals x squared minus 2x, and I want to know f of negative 3, I just need to replace all of my x values. All of my x values need to be replaced with negative 3. Simplify or evaluate. What operation am I going to do first? Okay, what's negative 3 squared? 9. What am I going to do next? So what's negative 2 times negative 3? Positive 6. Which means that f of negative 3 equals 15. And that gives me an ordered pair. My x value is negative 3. My y value is 15. And that's my ordered pair. I just found a point on my line. I found a solution to that equation. Okay, so there's my ordered pair. All right, there's my solution. I plug in negative 3. I solve for x. I get a solution. F of negative 3 equals 15. That also gives me a point on my line. I know the point negative 3, 15 is on this line. All right, so that's solving function notation using an equation. Now I'm going to solve function notation using a graph. Okay, remember, that f of that number, whatever that number is, that's saying, hey, that's my x value. And it wants to know what's the y value that goes with that x value. Okay? So if I'm given a graph, okay, this is a nice funky cubic graph for us. All right? I don't know what the equation is, so I can't plug those numbers into an equation and solve. But I can look at the graph. And I say, okay, f of 5. Well, that's when x equals 5. This is when x equals 5. So I need to look. Okay, well, where's 5 on my x? 1, 2, 3, 4, 5. And I ask myself, well, what is y when x equals 5? And so I look to see where my graph is. Right there. Okay? So that point is where x equals 5. X is 5. What's my y value? Close. 7. Okay, so my point is 5, 7, so that means that f of 5 equals 7. F of 5 equals 7, because I have the point 5, 7. When x is 5, my output is 7. Alright, f of 4, I'm going to do the same thing. I'm going to look for when x is 4. 1, 2, 3, 4, and then go up and see where my line is. So what's f of 4 equal? 3. Okay, let's look at negative 5. What is f of negative 5? Negative 1. 1, 2, 3, 4, 5. Okay, and then I'm down there at negative 1. And then f of negative 6. 1, 2, 3, 4, 5, 6. So look at the graph, f of a number is saying, hey, x equals this thing. What does y equal? X equals this thing. What does y equal? Solve for that value. Locate it on the graph or plug it into the equation. or maybe you have a list of ordered pairs. Okay? Let me actually, because I think it's my last one, let me just take a minute to do this. I think it's worth it. Let's go back to these beginning sets back here. Okay? I have these relations that are functions. Okay? And I say, well, what is f of 2? So when x is 2, what is y? Based on this list of ordered pairs. 3. And what's f of 4? 9. What's f of negative 4?
9.
What's f of 10? Negative 5. All right, questions on, you got your assignment, due Sunday at midnight. You got 10 minutes to start it.